Okay, so what were the important lessons that we just learned? Well, we write all of the equations of classical mechanics in terms of vectors. Why do we do that? That's because all vectors transform in exactly the same way. So a vector equation will take the same form in every single set of coordinates that you choose to use. So in particular, if I've got f is equal to ma, and I do a rotation, after that rotation, I'll have f prime is equal to ma primed. We also learnt that the dot product is in fact invariant under rotations. So x dot x is equal to x prime dot x prime. And I don't want to mislead you here. In fact, if we have a vector A and we take the dot product with the second vector B, this would give the same answer as A prime dot B primed, where A prime is the rotated version of A and B prime is the rotated version of B. So the dot product between any two vectors is invariant under rotation. You should be able to check the second equation. So check if you can do a calculation to verify that this is true. If you're not able to check that equation, it means you haven't understood yet, and you need to think some more about this. Every single fact that we state, you should be able to check with a calculation. So please hold yourself to that high standard. Every single fact that we state, you should be able to check with a calculation. Okay, so that's all I wanted to say about classical mechanics. Let's continue now to Lorentz invariance. Now, to discuss Lorentz invariance, we are going to generalize our story a little bit. We're not just going to discuss 3 vectors, we're going to start talking about 4 vectors. So we're going to imagine that we're in some frame with time t and position x, y, z, and we're going to move to a second Lorentz frame with time t primed and position x prime, y prime, z primed. Okay, so let me write down an example of a Lorentz transformation. So here are my primed coordinates, and I want to write down a Lorentz transformation, a very simple one. So there's a cosh phi, sinh phi, 0, 0, sinh phi, cosh phi, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And this would multiply into t, x, y, z. So the idea here is that I have a reference frame. So here it is. I'm going to call this x. I'm going to call that y and z. And I've got a clock for t. Now, I'm making sure when I draw this that I've got a right-hand coordinate system. And in particular, this means that if I take x hat cross y hat, this is the usual cross product, that will be equal to z hat. So you should be able to check this using the right-hand rule. Make sure that you can. Okay, good. So let me remove that. So make sure that this coordinate system is a right-handed coordinate system. So the cross product works exactly as I said. Let's put in our second coordinate frame. So here we have y primed, x prime, z prime, and there's a clock here. Let's call that t prime. Now notice something. If I look at this matrix equation that I've written down, then y primed is equal to y. So if I was to measure y primed is 1, that would correspond to a measurement of y as 1. If I was to measure z prime as 1, that would correspond to a measurement of z as 1. And that's why the y and y prime and z prime axes are perfectly parallel. We'll be assigning the same y and z coordinates in the 2 coordinate systems, and that's reflected by the fact that this matrix representing the Lorentz transformation has got 1s on the diagonal. Now, when you study Lorentz transformations, you might have been used to writing it in terms of the velocity. So how is the velocity appearing here? Well, the velocity is related to phi. So if I take the velocity of our v divided by the speed of light c, this is equal to the tanh of phi. Now, remember, for us, we work in units where c is equal to 1 is equal to h bar. So I'm not going to write the speed of light anywhere anymore, but I just wanted to show you that v over c is equal to tanh phi. And let's see why that's the case. So let's imagine that the XYZ T frame is at rest. So this frame is at rest. And now we want to measure what is the velocity of this primed frame. Well, what we can do is we can look at the origin, which I've colored as a blue dot, and we can ask with what speed is the origin moving. Well, from the matrix that I've written down here, we know that y primed is equal to y, z primed is equal to z, and x prime will be equal to sinh phi times by t plus cos phi times by x. And the origin is y prime is equal to y is equal to 0, z prime is equal to z is equal to 0, and x prime, which is sinh phi t plus cos phi x, is equal to 0. So I can actually now solve for x. X will be equal to minus, it will be sinh over cos, which is the tanh of phi times by t. And of course, this is nothing but minus vt. So we see, okay, I've said c is equal to 1. We see indeed that the velocity is tanh phi. And we also see that the primed coordinate system is moving away from the original coordinate system along the x direction. Because we move along the x direction, we call this a boost along x. Okay, so this relation between these two frames is a Lorentz transformation. What Lorentz transformation is it? It's a boost along the x direction. What is the full group of Lorentz transformations? Well, the full set of Lorentz transformations is the set of all boosts and all rotations. So the set of all boosts and all rotations is the complete set of Lorentz transformations. Let me just mention one more thing. This parameter phi is called the rapidity. So phi is called the rapidity. And you might remember what tanh phi looks like. So if you study what tanh phi looks like, as phi goes to infinity, tanh phi goes to 1. And as phi goes to minus infinity, tanh phi goes to minus 1. So if you study what does tanh phi do, it goes between 1 and minus 1. At this asymptote over here, the velocity is tending to the speed of light. And at this asymptote over here, the velocity is tending to minus the speed of light. So phi can range from minus infinity to plus infinity, and the velocity only ranges from minus c to c, minus the speed of light to the speed of light.